Welcome to the Walton Pi. Today we're going to be talking about how we can tell if a given collection is in fact a basis. So let's suppose that X is a set and B is a collection of subsets of X. Then B is going to be a basis for some topology on X, not necessarily knowing what topology, but is a basis for a topology on X, if and only if it satisfies these two properties. First, if B1 and B2 are two members of our collection with a common point X, then there is going to be a member of our collection, say call it B3, which also contains X, and B3 is a subset of B1 intersect B2. And two, the union of all elements of our collection B is X. If B satisfies those two properties, then it's going to be a basis. Let's go through a proof. So if B is a basis for a topology on X, then the union of all basis elements must be X. And if we have B1 and B2 in our basis, then B1 intersect B2, or with B1 intersect B2 not being the empty set, then there's going to be some B3 in our basis, where B3 is a subset of B1 intersect B2. Since B is a basis, those are both properties of a basis, so that means if it's a basis, it satisfies those two conditions. So now let's suppose that B is a collection of subsets which satisfies those two properties. Let's define T, so this is going to be the topology. Let's define T to be the collection of sets which are able to be written as a union of elements from B. We are going to show that T is a topology, which tells us that B is going to in fact be a basis. So note that X is the union of all the B's in our collection B, and the empty set is the empty union. So that tells us that both the empty set and all of X are both in our proposed topology. Second, if we have a subcollection U of B, then the union of all of those elements is going to be a union of elements in B, so it's also going to be in our proposed topology T. So we have empty set X and arbitrary unions. Now we have to deal with finite intersections. So note that if we want to show it's true for finite intersections, it actually suffices to show it's true for just two elements. If that's the case, then we're able to go through and just inductively build up to any finite intersection that we need. So let's let U and V be in our proposed topology T. If U intersect V is empty, we're done. Otherwise, let's let X be an element in U intersect V. Then that means there are going to be proposed basis elements BU and BV, where BU is a subset of U, BV is a subset of V, and BU and BV are in our collection B. Then X is in BU intersect BV. So that means there's some BX, which is a subset of BU intersect BV. That means we can write U intersect V as this union over all X's in our U intersect V of the BX's. So that means we've written an intersection as an arbitrary union of elements from our proposed basis B, so that tells us that T is a topology and B is a basis. I hope that video was helpful in understanding how we can tell if something is a basis. If it was, please like and subscribe, it really helps me out, and leave comments down below of other topics you would like me to cover. As always, I hope you have a great rest of your day and good luck with all of your math.